Today I'm going to talk about data science and the kernel density estimation in order to group data. So for example, to make tier lists or to group certain amount of data that share similar values in one dimension. So imagine a problem with 1,000 employees who want to be sorted into tiers like 3, 4, or 5 tiers in order to evaluate their performance to get a certain reward like a yearly bonus. And so what a human would do is to fix certain intervals, like between A and B it's good, between B and C it's excellent, and above C it's perfect. But several problems arise with this solution. Doing that forces you to reevaluate the intervals yearly, because the performance of the crowd can change. So the average will change, and the variance will also change. So this is also very arbitrary, because it's you who chooses the ranges, and finally you can have intervals with little to no elements. Like if you expect your employee to score to be equally reported, equally distributed between all the 3 tiers that I said earlier, you might end up with no one being perfect or no one being good or something like that. So if you want to group a system, if you want to group a samples like 1,000 employees, you have to you can either use the naive solution, or you can build a system that is objective in order to group data together, in order to have a certain amount of employees that are between A and B, a certain amount of employees that are between B and C, and a certain amount of employees that are above C. So and that way the system will be dynamically selected between the performance of all the employees. So a first remark is that it's analogous to a problem with a histogram. So the histogram is a problem with bars, in which you can have either uniform bins or non-uniform bins, like depending on the size you want to have on your chart. And secondly, it's very useful in algorithmic to automatize the decision. The first example comes from a video that I've encountered. Certain players have been assigned an elo, and the author wanted to sort them into tiers, and say, okay, this player is going to this tier, this tier, this tier, in order to present better his analysis. So in order to do that, he shortly explained that he used an algorithm, but he did not explain in depth what's going on. So I thought it was a good idea to present the results and the methodology. So the code is freely available on his GitHub. So I took a knowledge of his work and tried to see what's going on and improve it. So let's do a bit of mathematics. So if we we use kernel density estimation. So it's a method to smooth data from samples. So you have discrete points, so samples, and you want to translate it into continuous distributions. So discrete to continuous. So if we have n samples of xi, sample points, we call f of f depending of x, with also h being a parameter, the function, such as below. So to two things arise. The first thing being h, the smoothing parameter that we call bandwidth or fenêtre, and k, a function called a kernel or noyau. The function f is function of f, so it's a distribution function, a continuous distribution function, well, continuous by parts function, and we use this to represent a certain distribution of our system. So we have multiple kernels that exist. So I took this data from the scikit-learn, which provides a lot of data, a lot of elements, documentation of kernels. So you can see that near the center of in the top left, we can see that we have the 6 distributions centered around the 0, so between the expected value, and depending on what we want, we can represent it in multiple ways, either a Gaussian, a top hat, a Panichnikov, exponential, linear, cosine. So what might arise is that some of these functions have an infinite support, meaning that they are defined between -infinity and +infinity, which can be problematic. But often we use a truncated Gaussian. We don't care about the infinitely small amounts of parts that are out of the range. So it's not really a problem in computer science that we have a certain part that is neglected. So we use a truncated Gaussian to present it, but it's not really a problem. Just it's important to know that there is a certain part of the Gaussian that might be not considered. Like, for example, if we see the performance, it is possible that since we have a Gaussian, there is a non-zero probability that you have a negative performance score. And if you have a performance really close to 0, and a lot of people score this performance, you might have part of the probability that goes in the negative, which is something to consider when you do this sort of analysis. Okay, and often in this kind of analysis, we use the Gaussian kernel because it's very convenient, and due to the central limit theorem, we can say that it represents the best the experiment. So, as an example, here we have an example from Wikipedia for a one-dimensional problem in which we have certain dash, as you can see on the left diagram, left histogram. We have 1, 2, 3, 4, 5, 6 values that are in the chart. You can see that the histogram does not represent it well, and we see on the right density graph that it's represented a bit differently on the density function, the kernel density estimation. Okay, so we have done that, and how does that help us to make tiers? So the task is to make an algorithm of decision based of the video I linked, and we will try to explain every step and to apply it to various types of data. When I did research for this video, I found a paper from Silverman who used two datasets. One dataset A, that is the length of treatment spells of control patients in suicide studies, and B, eruption length in minutes of 107 eruptions of Old Faithful geyser. So this paper was really interesting because it was taking about how to represent some kind of data, and I thought it was a good idea to use this example as kind of verification of my algorithm. So the dataset A is represented here in a table. So we see that it's distributed kind of like a log normal. Like it's something that I've stumbled across when I analyzed speedrun data with a peak that is near 0, and then a long tail near the infinity. So the support would be 0 to infinity, and we can see that it's not symmetrical. So to represent it, it's kind of hard to like say, oh, it's Gaussian or something like that. And we can then try to find groups. So if I wanted to have a naive solution, in this case, what I would do is to make a group from 0 to 200, which represents the big spike at the beginning. Then a group between 200 and 350. And maybe it's very confusing to see what we will do after 4,000, because we have really low samples. We have only few values, like as you can see on the table. So it's very difficult to argue where to put those limits. So in this data set, we have few different ways to represent it on the Silverman's paper. So with certain kernel estimates, you can see that depending on the parameter h, it is represented quite differently between on the top of the figure 2.9, we have either with 20 or 60, and at 20 we can see that it's really bumped, while with 60 it's really smoothed out. With other kernels that I will not talk in this video, we have different representation, as we can see on figure 2.11. On the dataset B, we have a table that I almost have hidden in the top part, which is not really interesting. Here are a few representations. So on the left, we can see a naive estimate. So it's just a histogram with very low valued, really low valued h. On the right, we have a kernel estimate, so Gaussian. And on the bottom, another method that I will not talk about, the nearest neighbor estimate. So the algorithm is inspired from the video. It computes a density kernel, then it computes the log probability, log of the probability of the function, and it finds the local minimums, and then with these local minimums, it sets boundaries to the tiers. So to summarize, it finds where there are less values in the density. So we will try to improve this algorithm and to validate on other datasets. So this is the algorithm originally. So the author used a list called elo_list. Then he puts it into a CP object called Kernel-Density, and adds it with a bandwidth k that is an argument, and by default 10. In his problem, he didn't have to change k, so he didn't even care. He then puts the KDE, kernel density estimate, into a function score samples that will give him values in the space that he called space. And then he found the minimum using a arg_rel_extrema, and then he plotted this on a matplotlib graph. So my version is a bit different. So first the imports. So I import numpy, I import matplotlib, and oops, I forgot in the second line I forgot a enter key to go back to the line. So import numpy as np, import matplotlib as plt, and from sqlearn.neighbors import kernel density. Oh wait, yes, And finally, from CP signal, import arglextrema. So this slide is a bit of a mistake, so okay. And then after, I use the long command to just put all of my sources, because it helped me to like find them quickly if I close the tab or something like that. So the pre-treatment is quite easy. So we have text. So the texts are just copy-pasted from the PDF file of Silverman's paper. They are floats with 2 digits, split with a space. So to do that, we just use a quick treatment function that will just split the long character into a list of strings, and then we turn it into floats, and finally we turn it into an NumPy array, and this NumPy array is then reshaped to fit the requirements for the later algorithm. Don't ask me why, I just know that you have to do this, else it crashes. I tried to remove it and it didn't work. So do the reshape at the end. So first part of the treatments, we build an algorithm. So the first argument is D. So D is a list of reals. So in this case, we will only consider the one-dimensional case in which we have just a list of values, but it can also be vectors. So it also has to be considered. We also have the argument K that is very important. It's what we call H earlier. It's the bandwidth. And the type of kernel. So if we choose Gaussian, which is a good idea in this case. I tried to use other types of kernels. It didn't seem right. Like it seemed very off. And we can also design the number of values in which we plot the log probability. The value given by the author of the original algorithm was int of, so the integer of the range, double of the range, well, the double of the range of the values. So it was not a good idea. Like, I mean that I have no reason to not use it, but I don't have a good understanding of what's a good value. So I just added an argument because I wasn't sure if I had to keep his values or not. So I just like say, okay, if I don't want, I do a 0 or not. So the algorithm starts with finding the minimum and the maximum values. Then we call noyau, so our kernel, being the kernel density object from CP with the bandwidth K and the kernel noyau. And then we fit the kernel with our data. And the object noyau now contains the data D. And then we have to score the samples later. So then we will try to find the values from which we compute the values and from which we graph. So the algorithm previously said between the minimum value of our samples, the maximum values. As I said, between the Gaussian that has an infinite support, like if we do this, we truncate, like we only show from minimum and maximum, but you have to know that there is a non-zero probability to go below min and above max if you choose a Gaussian. And then we score the samples on the axis. Don't forget the reshape, because else CP will be very angry. So the second part of the treatment, we find the extremum, so the local minimums. We could also have used argral min. So basically, what it did was returns both the minimum and the maximum, but in reality, we just need the minimum, so it can be faster, but it doesn't really matter. And something that I was really surprised is that in his analysis, in his algorithm, he didn't put a fail-safe in case there are no minimums, like there are no points that is very different from the other, which does happen. Like from what I've tested, the fact that there is no local minimum, like I'm talking about a minimum in the centers or things like that. So in which means returns nothing, so the empty list does happen, and it's not a bug, it's a mathematical problem in which the algorithm used by CP actually is correct. There is no discrepancy between other values that you can call it a local extrema at all. So so it's actually quite good that that I added a error raising, exception raising, in case the means was empty, so the minimums were empty, and it means that the k is chosen incorrectly to not represent correctly the function. And it's very important to do that, and maybe in his problem he didn't encounter that, he assumed it was a bug, but it's not a bug, it's actually mathematically correct. What it is was mathematically correct, but he had to say, okay, if it's empty, it means that my log probability is almost constant and does not have any significant bump. So it's like if you have a uniform density. So I think it's important to add this error raising. So just a function quickly to plot. I just added a title to I put titre as a title in the as an optional argument in the function, and I also put the value of k in the title of the graphs, because it's actually what matters for me, because the author used k as 10, but he also said that you can play with, and actually he's right, because doing that changes the number of intervals. So for the dataset B, which I started with, if you put a k above 0.5, it returns no local maximum because the function is not smoothed out enough. It's too smooth, so it's almost constant, which is a problem I described earlier. If you put 0.4, it looks like the top middle diagram, in which you have a minimum at 3, and then the less and less you smooth the things, the more it represents the sample data, and the more and more you smooth, so the more and more k value is, the more and more you smooth the function. So we can see that between all of these values, they both agree that near 3, so near 3, there should be 2 groups. They did not say 3, they did not say 4, they did not say 5, they did not say 1. Well, 1 is not possible because I say it's a problem. So here all of them agree that there is a strict distinction between the samples that are below 3 and the fact that are above 3. What's interesting is the point with k is equal to 0.01, in which the minimum is actually shifted. I think it's because of the fact that we don't smooth enough, and that it turns out that if you smooth less, there are more values near 4, so it shifts it a bit. I was really surprised by it. And above, yeah, so we have 2 groups, one below 3 and one above 3. In the bottom right, we can see the naive estimate from earlier of this dataset B. And we can see that, okay, it's fair enough that you have one group on the left and one group on the right. So for the dataset A, so if we start with k is equal to 1 or below, you have this weird shape in which you have a lot of single valued interval, which is not very interesting because like if you have one interval for each value, it's not interesting. It's just if you have all groups with only one person, like it's not a group, it's just the individual on himself. We can also see that at 500 we have no values near, so the log probability drops down dramatically. And then the more and more we smooth the function, the less and less we have local minima. So we see that in our algorithm we have in k is equal to 10, we also have one weird one that looks like a maximum, but it's actually returned as a minimum. So I think it's a stable point. I don't know if it's called like this in English. So it looks like a minimum, but it's not really. But numerically, it thinks it's a minimum. Near 250, we have this weird point that looks like a local maximum, but it's not. And we see that with k is equal to 10, we still have a lot of intervals, and so we want less. And the further and further we increase the k, the less groups we have. So we see that with k is equal to 40, we have two groups. Well, we have three groups. We have one below 500, one between 500 and 700, and one above 700, but it's not really convenient to use that because we have no points above 700. So it's a local minimum, but it's local minimum because of numerical errors. And if we go at k is equal to 100, we find only two groups, one below 550, 550, and one above 550. So in this example, we see that it kind of fails because either you have points that are too close to each other with k is equal to 1, and the more and more you smooth out, the more and more error you create, so that with k is equal to 100, actually the algorithm is really bad because you will have one group that has a lot of samples and one group that has almost none. With k is equal to 10, it's fine, but like we still have lots of errors, so it's not very convenient. So in cases like this, it can occur that it's a bad idea. So I don't know if it was the case in his algorithm, in his values, in his algorithm that he used. But to me, it seems like for certain examples, there are cases where it's a bad idea. And also, I did not find a k that was better than this. And I think it's possible to find a k that is between like 10 and 40 that would represent it fine. So I won't invalidate the algorithm. I just think that you have to be really careful of the k value that you pick. We can also see that on the k is equal to 40, we have some kind of local minimum, but like it's like the derivative, the slope is really low, but it's not detected as a local minima because it's not increasing. But it would be interesting to find out to put a limit at this point. Okay, and that concludes this video. So we have analyzed an already existing algorithm. We described mathematically what we were doing, and we have commented using two use cases how they can be used. It's useful for automatization of tasks, algorithmic, artificial intelligence, machine learning, and decision making. Thank you for watching. Goodbye.